So I'm going to talk about recent work. It's still not yet published, but it will appear soon in a paper. And what I'm going to talk about is some ideas about gravity and cosmology. And I think we need a new paradigm to think about this within the framework of string theory. First of all, I will not be really using string theory in all detail. What I'm going to assume, namely, is that string theory is based on general principles. I'm also going to assume that string theory has something to do with the real world. You may not agree with one of these, but I think it's quite one of our things we like to believe in. And then better yet, we can think about string theory as something that follows from general principles which apply to the real world. So I'm going to use string theory as a source of inspiration to think about those general principles and apply them to the real world. And one of the motivations for doing string theory is to understand what gravity is. And there's many properties of gravity already discovered within string theory, but there's one mysterious fact, namely gravity is a macroscopic force. We see it at large distances, but somehow it knows about the microscopic states. Somehow it counts states. It has the information about the UV. Why? Why is that the case? Is this because there's some conspiracy between UV and IR, or is there a principle at work? I'm claiming, of course, a principle. If we see two objects in space and we think there is a force between them, we may describe it in terms of some force field. But sometimes there's another reason. Namely, there can be other degrees of freedom that are relevant for it. This was two nuclei being bound together in an atom, and we know that the way that they're bound together is because there are electrons, and the reason that the force appears is because these nuclei influence the phase space of these electrons. You can integrate out the electrons and get some effective description, but it's a very different way to think about a molecular force from electrons than by doing an effective description. I'm claiming gravity has a similar description in terms of other degrees of freedom that we generally ignore, and there will be situations when this picture will be different from the usual description. So the outline of the talk is as follows. I'm going to motivate this proposal from black holes and string theory and input from matrix theory. This is going to be a motivation because I'm going to be interested in the general principles that I'm going to extract from it. And so I'm going to then explain to you what is an adiabatic reaction force, because that's going to be the way I'm going to think about gravity. Then I'm getting to this hidden phase space. There's a certain part of the phase space in our universe that we're not using in everyday descriptions of physics, but it will be very important in understanding where forces come from and where gravity comes from. It's a hidden phase space that we're going to quantify. And indeed, I will show that inertia and gravity can be interpreted as adiabatic reaction forces. They're a very different way of thinking about the origin of these forces. And finally, I'm going to end with what you probably call speculations about dark matter and dark energy. I believe in these things, so I would like to put the word speculations in quotation marks. So I'm going to start with a study that we did, there was actually a previous string conference I talked about this, gravitational collapse in ADS-CFT. We can study how a neutron star in ADS-CFT collapses when you put too many fermions on top of each other. Something happens to the phase space. I mean, these fermions cannot just undergo collapse and sort of end up in a point in space. There's some way you have to preserve phase space. And we studied this. And in ADS-CFT, you can think about the fermions as composite operators that you build out of traces of some matrix-type variables. Now, what I'm going to tell you is standard lore, I think. It's just general things we know about. Namely, what happens to these traces, or what happens when we undergo gravitational collapse, is that we have to keep track of the individual bits that's inside these traces. They're sort of the D-brain states that we have. So I'm going to describe it in some qualitative way, but you probably recognize all of this from your knowledge about string theory. So the Fermi statistics, that basically excluding the volume of all these fermions, is modified in string theory. What we do in string theory, we think about the objects that make the fundamental bits of these operators, think about them as D-brains. And with D-brains, you don't have just statistics that exchanges them. There seems to be a way in which you can make linear combinations of states in such a way that you, instead of having Z2 as your statistics, you have a U2 group. which involves the U1 of phase rotations of each of the states. And this has very important consequences. The consequence is that the positions of the d branes are no longer just coordinates for each of the branes, but you get a matrix-valued coordinate field. And I think about this basically because there's matrix elements between two d brane states of the coordinate operator x. So I'm going to think about these matrices not as being the fundamental fields, but as being expectation values of certain coordinate operators. And if you have n of them, you get an UN symmetry. Of course, we know this, but this is the way that the additional phase space is going to be found, because there's additional coordinates that we have introduced, which is going to be responsible indeed for gravity. This we know very well. If we integrate out these open strings, because that's basically what I've been describing between these d branes, those are the off-diagonal modes, and integrating them out induces gravity. We know this very well. The eigenvalues on the diagonal are the positions of the d branes, and you can think about this either in string theory or, well, in some matrix-type model. And here I wrote down a Hamiltonian for the matrices, and indeed you sort of know from this Hamiltonian that when we integrate out off-diagonal modes, that we get well, the usual gravitational force between those particles. I just want to use this as a general picture in string theory, because I want to go to the sort of what is the principles behind this. But we do know the following, that when we are undergoing this gravitational collapse, the states will not stay localized on the diagonal, because this is where the positions would be of the objects, of the particles that we have. But we start making longer traces, and the short traces that describe these particles become long traces, and we're filling up the entire matrix. And this is how you go from a phase where the states are both basically close to the diagonal to a phase where the whole matrix is being occupied, sort of in a deconfined fashion. So a black hole is something where all of these degrees of freedom are equally occupied, and this is why we start losing even track of what space-time is, because the positions are no longer recognizable as individual eigenvalues, the coordinates become matrices, and we lose the classical picture of space-time. So the degrees of freedom that are responsible for gravity are indeed the degrees of freedom that have to do with the emergence of space-time itself. So gravitational collapse is like where we see matter disappearing behind the horizon, but the opposite phenomena where you get matter out of the horizon is what we call emergence of matter. Now, an important thing that I'm going to use later on is that I'm going to quantify the amount of energy that's situated in the off-diagonal modes. Namely, the off-diagonal modes are responsible for the gravity or self-gravity of these eigenvalues, and there's a positive energy in this, which is the gravitational self-energy of an object. It's expressible in the Newton's potential, and it's positive. And you may wonder why it's positive, because generally we think about gravitational energy as being negative. The reason is that actually the energy in the eigenvalues goes to zero when you start collapsing, because you subtract the potential. But then there's a positive component, which is this is like basically the energy in the gravitational field, like we have in electric field also some energy. So this is the picture you should have in mind. If you have two objects together, you actually include the potential due to both of them, but if you subtract then the potential energy here and here, you do double counting, so you have to add a positive gravitational energy, which is the energy contained in these off-diagonal modes. So now you may think I'm describing everything in terms of matrices, but actually that's not the end of the story. As I told you, there's actually some states. I want to think about these matrices as expectation values of certain states. But we also know in string theory very well that we don't keep those eigenvalues always as good coordinates on the space. And one way to think about it is that if you look at an object near a black hole, I can try to describe this in terms of these matrix-type variables. Then this box, for instance, would be described by a part of the matrix. But then there are also strings that stretch between the box and the black hole, and they are off-diagonal modes here. Now, what happens when the box goes into the black hole, this gets thermalized, because this is a thermalized state that's describing the entire black hole. So this is where the whole matrix is being used, or actually it's much more complicated than just a matrix, because what happens when these off-diagonal modes acquire an expectation value, you have this kind of term in your Hamiltonian, and this means that the eigenvalues get a potential, and the potential gets lifted, and we enter into what's called the Hicks branch. This is just standard law. So what's really being described here is what's called the Hicks branch, and it's a much more complicated set of dynamical equations. And this process of going from the Coulomb branch to the Hicks branch is really what gravitational collapse is about. One important thing I will need later on is something about the size of this matrix. How big a matrix do I need, and how many of these eigenvalues do we associate with a box with a number of particles? And there's a proposal I'm going to make which is based on not really a string theory calculation, although there's actually a matrix theory answer to this which I'm going to use and connect to. But I'm going to use an old argument by Bekenstein, who basically thought about precisely this situation. He said, what is the maximal entropy that you can associate with a box of matter with mass m and the size r for the box? And he used a thought experiment. He said, let's put this box very close to the horizon of the black hole and let it drop in from a certain, well, the closest distance we can put it in. Then there's a certain amount of work that you do in order to get the box into the black hole, or pull it out if you wish. And it's equal to mgr, so r being the distance, m the mass, and g is the acceleration near the horizon. And you can then extract what's the change in entropy by just writing it as T delta S. Now we know that the temperature near the horizon is equal to the acceleration divided by 2 pi, and from that you extract that the entropy cannot be bigger than this amount, and if it's an adiabatic process, it's actually equal to that amount. So lowering a box very slowly into a black hole, and then sort of the last bit you drop in, you expect that this would be the increase of entropy. And this says something about the maximum number of degrees of freedom that you can associate to this box. And indeed, this number, mr, is going to be the proposal of the size of the matrix. Actually, it's a proposal that already was made in matrix theory, as I said. I mean, there was a paper by Banks, Susskind, Erik was on it, and I think Willy Fischler. And they proposed indeed a model for black holes with precisely this amount of eigenvalues or size of the matrix for this box. So this is going to be the picture for me of something dropping into a black hole. I'm going to use a description for the matter that's outside. And I think there's part of the whole system also describing the black hole. This is, you can think about as something that's not yet thermalized, because when it drops into the black hole, this part will fall into the black hole. This is called the Coulomb branch, and it's described in terms indeed of these eigenvalues and of the off-diagonal modes that are responsible for gravity. When you throw it into the black hole, of course, all of this becomes one big object. But I'm interested in to study what happens when we sort of near the situation, and then we'll find that the temperature of the black hole, for instance, will start heating up this part, and eventually this also will be heated up. And this will do certain things with the dynamics of, for instance, these eigenvalues, and we'll also sort of, well, should get a quantitative then idea of what happens to the gravitational field in this picture. The equations, as I said, are not very specific here, but we do know certain examples. We don't know examples which are supersymmetric, and then we can figure out precisely how many states a black hole has. And then we count those states on the Hicks branch. But there's also the Coulomb branch, and I like to think about this in sort of a graphical way as follows. This model is this is modeled on what I know about the moduli space of instantons, because there's certain supersymmetric black holes where we can count states by using the moduli space of instantons. If you have point-like instantons, then they sort of like are a corner of your moduli space where all of the instantons are localized as points in space. And this is where the moduli space looks like the symmetric product of your target space. And this is where sort of the particles are living, and you can sort of see the usual sort of semi-classical picture of particles. But when the instantons get bigger, you get some Hicks branch, and that's much more complicated. So this is going to be my picture of the phase space. The black hole states are all living here. The matter states that's falling into the black hole are here. The reason why the particles go into the black hole is because there's much more phase space here. And this is why there's a force going that direction, because there's a general principle that tells you that force goes in the direction where the phase space will increase. And this is where, indeed, the adiabatic reaction forces come in. Because there's a general principle. When you have a fast dynamical system and you influence it with slow variables, that means you're driving it, you're changing the phase space volume, you get a reaction force. This is precisely what happens in molecular forces, for instance. And for that, you need that the time scales are very much separated between the slow dynamics and the fast dynamics, because then there's an adiabatic approximation. And in that adiabatic approximation, the force can be determined from the principle that phase space volume is preserved. So this principle I'm going to use, actually, and I'm going to use the answer that we have, namely gravity, to determine now, later on at least, to what is the phase space volume responsible for this force. But let me explain this principle a little more detailed, and actually going to first do it in a very trivial example, something with 1 degree of freedom. Say a harmonic oscillator, which changes slowly as a function of a variable which I call x. You can think about this harmonic oscillator as being one of these off-diagonal modes in the matrix, and indeed they are described by harmonic oscillators, which depend on the distances between those d-branes. Then if you do it very slowly, the eigenvalues just, well, vary as a function of x, but they never cross. And this is important because then you have an adiabatic invariant, which is basically the level, the mode level of your harmonic oscillator. And this is the Bohr-Sommerfeld integral. And this is actually an action integral, but it satisfies very much similar equations as we know from thermodynamics. Of course, this has nothing to do with thermodynamics, but there's an equation that looks like the first law, but where the temperature is replaced by the period of the motion. And the force can now be written as, well, the derivative of this energy as a function of the variables j and x, but you keep j constant, because that's an adiabatic invariant. But using this equation, you can also write it in this form. I'm going to use this later, because there's a generalization of this when you have, of course, many more degrees of freedom. Because there are many harmonic oscillators, and they may be interacting with each other, and then you have some complicated dynamical system. But then you can still have an adiabatic invariant, namely the volume of phase space below a certain energy state is constant if you slowly vary the Hamiltonian. And the reason is that the number of states below this energy state stays constant. So the number of states is equal to the volume of phase space, and this therefore has to be an adiabatic invariant. So you're assuming here that eigenvalues do not cross, which would happen when you start changing the system more rapidly. But here we can indeed define an entropy by taking the standard formula, and you have the standard kind of thermodynamic relations, although we may still be considering a pure state. This is a Born-Oppenheimer situation where you really just slowly vary the state of your system. But you can write down similar equations given the adiabatic invariant, which is the entropy now, and you get the usual sort of thermodynamic or entropic force, although, as I said, it's a Born-Oppenheimer force in this situation. When it becomes an entropic force is really when we are in a thermodynamic situation, and this may happen when the separation of time scales starts to break down. So I'm going to use this actually to extend what we know about black holes, where we are in a thermodynamic situation, to situations when we're not near black holes, because I'm going to generalize the notion of entropy basically by this formula. I mean, I'm going to say it's the amount of phase space when I'm in a certain state below a certain state with a certain energy, well, just obtained by integrating the volume of phase space. And this may be in a situation where there's not really a temperature, a finite temperature situation, it need not be thermodynamic, but it's just a phase space argument. Just to already announce something, I mean, there's generalizations, of course, of this adiabatic approximation when you include higher order corrections. And they're quite interesting because if we look at the first order correction in some systematic expansion in the slow variable that you're changing when you change the dynamical system, then the first correction to it is actually an electric force or magnetic force due to the Berry phase. So in Born-Oppenheimer, you can slowly change your states, and then you can introduce a Berry phase, and there's a magnetic component to the force, which is the first correction. Another thing that can happen is that eigenvalues start crossing. And then it turns out that you can parameterize actually this crossing by a 2x2 Hamiltonian, which we can, well, just for the sake of the argument, use coordinates in here. But then it turns out that precisely at the origin, this Hamiltonian degenerates, and this is where the eigenvalues cross. You get then a monopole field. So the Berry phase has a monopole field. By the way, these are the same kind of equations that we use to describe sort of things like not just monopoles, but also instanton type equations. Namely, if you have an instanton, you can also construct a Berry phase, and then the Berry phase actually describes you well, a certain gauge field on that. It's called, that's actually in the ADHM construction. But the thing I wanted to point out, namely, is if there are more eigenvalues crossing here, there's also a non-abelian gauge field. The number of eigenvalues that cross here, you can define a non-abelian Berry connection, and that defines for you a non-abelian gauge field. So it's almost like what we know from D-branes. If I have an object with a monopole charge equal to n, then I should expect a UN gauge field living on the locus of this defect. So this is a general fact about just dynamical systems. This has nothing to do with string theory, but I think string theory uses these principles. Oh, what I'm doing here. So now an entropic force, this is sort of like an adiabatic reaction force or a Born-Oppenheimer force, but it's of course in a thermodynamic situation. The equations actually are very similar to what I wrote down before, except you can now derive them from some partition function. The reason I'm showing this partition function is that eventually I'm interested in a situation where I will have a finite temperature and I want to compute corrections. These equations are the saddle point equations, but one of the things that we know in statistical physics is that there are fluctuations around a saddle point equation. And for that I can use some partition function. But one important thing, by the way, an entropic force is still an adiabatic force, so it doesn't require entropy to change. You just use entropy as a adiabatic invariant to do your calculation. So this is just general facts. This has nothing to do with gravity so far. This is just general facts about emergence forces. Now, how do I want to apply this now to the situation with gravity? I mean, I'm going to think about a situation, some dynamical system with many degrees of freedom, where I generally don't want to keep track of them. I mean, we integrate out degrees of freedom all the time in all of physics. And I'm claiming indeed that in the microscopic description of this universe, there are many degrees of freedom that we generally ignore. We do this in Wilsonian way of thinking about quantum field theory. We take a UV cutoff and we integrate out everything beyond a certain scale, because we believe that does not influence the IR physics. This is based on some idea of separation of scales, but there's some mistake in that reasoning. Namely, if the slow variables that you're using influence the phase space that you've integrated out, you get a reaction force. So you have to keep track of the information or the phase space of the degrees of freedom that you've integrated out. You cannot ignore it. There has to be some way in which you use a bookkeeping device of the phase space of the fast degrees of freedom that you've integrated out. So how do we construct a bookkeeping device? I have a big phase space that I'm integrating out. There's a reaction force that I'm getting from it, and I want to keep a very sort of efficient way of describing what that reaction force is. I'm going to take an example, a toy model. I'm going to say there's a very big phase space, and I'm going to integrate it almost out, everything of it, and replace it by one single variable. And I want to choose that one single variable such a way that it still describes the same reaction force. How do I do this? Well, there's a very natural way to do it. If I replace all degrees of freedom by just one, I'm going to demand that indeed in sort of the thermodynamic situation, the partition functions are the same. So here is my big system with many degrees of freedom that I've integrated out. And I'm going to compute some partition function by just introducing a temperature. Now here is the right-hand side is just 1 degree of freedom. It has 1 p and 1 q, and it has an action that I just write down in the standard form, integral p dq and h dt. And I'm demanding now that the two are the same, these partition functions. I also, of course, want another thing, namely, I want that the reaction forces to the big system and of the small system are the same. You get a correspondence, namely between the entropy, when you calculate the saddle point here, the entropy here must be equal to the first term in here, because the second term, the energy are the same, and you find a correspondence between the temperature and the frequency, the Euclidean period, and the entropy and the action integral. So you get that the entropy of the big system goes over into the action of the slow system. This, by the way, is open-closed string correspondence. If I integrate out open strings, I can represent it by a classical term in the closed string. So this is a classical action, but this knows about the volume of phase space. There's no system in the world where one solution knows about the volume of phase space. The phase space is the space of all solutions. However, in gravity, we claim there's one solution, namely a black hole, that knows about the volume of phase space. And indeed, these equations, these correspondences, are exactly how we construct gravity. We map the action of the gravity onto the entropy which we associate with the microscopic states. And the reason is just that gravity is a bookkeeping device to keep track of the microscopic phase space. And you have to do it because it can create a reaction force. So this is the principle that explains why gravity knows about the microscopic phase space. So the conjecture is that gravity, or actually I should say inertia, is an adiabatic reaction force. Because we know that gravity is not really a force. I mean, it's inertia that's the force because the equivalence principles put them equal. So there must be some fast dynamical system that's underlying our universe. And inertia then should be thought of as the leading order adiabatic force. And there are other corrections to it. And they are the higher order corrections. And they may lead actually to other forces in nature. An important element in this is that the separation of timescales that's needed to do this adiabatic approximation starts to break down the horizons. And this is where we enter a thermodynamic regime, and this is why black holes behave like a thermodynamic system. So this was the intuition, and now go back to what I had before, this idea of string theory. So if I think about, indeed, inertia as a force, I can also generate this artificially by accelerating or by putting the system near a black hole. Then I have just Newton's law. But I'm going to interpret this force, indeed, as an adiabatic reaction force. Namely, what's responsible here for the force are the strings that connect this single eigenvalue to the rest of the system. And here I integrate out these modes. So these modes are the ones that sort of pull this object back into the black hole. And this, for me, is the polymer. This is the heat bath. And this is the bead connecting it. So this makes clear that in this way of thinking about black hole formation with a thermal state here and a single eigenvalue outside, that the reason why the eigenvalue wants to be in there is entropic, and it's just basically an entropic force. And you can calculate what is the change in entropy, or at least the would-be change, because actually entropy doesn't change, it's an adiabatic process. But if you then just write the force in this form of an entropic force, we know what the temperature is, it's just expressed in terms of the acceleration. And then you get that the entropy, when you differentiate it, actually can be expressed in this form. And here, by the way, you see already this action-entropy correspondence, because here actually the entropy behaves like an action variable, because this is precisely what you would expect sort of for a Hamilton-Jacobi type field. And this is going to be the principle that I'm going to use actually to generalize this argument, not just near horizons. I want to know what is the force also when we move away from it. Indeed, sort of think about a situation when I have a particle much further from the black hole or even some other object, then we know it can be expressed just in Newton's potential. But the idea is that far away, here we're not in a thermodynamic regime, but we are in a Born-Oppenheimer regime. And so it's still a Born-Oppenheimer force where we can extract the magnitude of the force from the knowledge about the microscopic phase space. So the inertial force should follow from the response of the phase space volume of the underlying dynamical system under these sort of virtual displacements. Now, it turns out there's only one natural answer. Of course, now I want to tell you what is the volume of the phase space responsible for this force. There's a very important boundary condition, namely the volume of the phase space should match with the entropy of a black hole. So I do expect that there Newton's constant will come in. It will tell us something about, well, when we're on the horizon, the phase space there should be A over 4G. So what is it here when I have a Newton potential that's different from what it is at the horizon? Because I can express actually Newton's potential in terms of a velocity. So I'm going to ask the following question. What's the total phase space volume associated with the region of space contained within a surface where I also know the amount of energy in the system? I'm going to express it in terms of Newton's potential, and actually I'm going to look at surfaces which are equipotential surfaces of that Newton potential. So I'm going to write Newton's potential actually as a velocity, so v is the escape velocity to infinity. So at horizon, v would be equal to c. And then actually a over 4g is just multiplied by v. That's the proposal. Because then if I take c, go to the horizon, I recover the usual formula. But this formula actually contains much more information and tells us about the volume of phase space for a much more general region. Actually, so you should think about this indeed as a generalization of the Bekenstein-Hawking formula. And I propose it as a conjecture, but it's the only natural way in which we can make things work. Yes? 5 minutes? Then you're going to miss the good part. All right. I'm going to give an interpretation of this phase space as follows. Namely, if I think about all the matter inside a volume, you can sort of separate it into energy quanta. I already told you the size of the matrix. But there's more phase space than just this number, because this A over A times V is actually bigger than this Bekenstein bound. And the reason is that I'm going to include not just the eigenvalues, but I want to include the correlations with the environment. So you should think about all of these eigenvalues as being connected by, say, by little open strings, but there are also connections to the outside. And then to count the phase space inside here, I have to project, sort of make sure that I don't have any entanglement between what's in here and what's outside, or just count it. And this you can do by inserting a complete set of states on the boundary. That complete set of states is like A over 4G. This is the number of energy bits. Actually, it's like L naught. This is like the central charge. And the entropy formula I gave is like Cardy's formula. And you can think about this as just counting partitions of this energy on the boundary states. This I'm going to skip because of time. Anyhow, this is just indeed a verification of the same idea, actually, where I calculate the force in a very general class of metrics. And anyhow, it's a class of metrics that would include Schwarzschild and de Sitter. And de Sitter is the case where I want to be interested in. Actually, I have a formula indeed for the temperature, because for the Sitter space, I know that this velocity v, which I have to put here in this form of the metric, if I put that equal to h0 times r, I get the Sitter space. And this would be the de Sitter temperature. And in that case, you can also calculate the entropy, and that entropy is a well-known formula. Namely, it's precisely what people calculated in the de Sitter space as being the holographic bound following Busso's prescription. So this volume of phase space actually saturates the holographic Fischler-Susskind-Busso bound, and it's expressed in terms of the Hubble constant. So it's actually, there's a constant phase space density. But I'm going to reach the important conclusion that the energy density in this dynamical system is equal to the energy density in our universe and contains also the dark energy. So the dynamical system is actually representing the dark energy. So something is happening at microscopic scales, and the energy that's happening there, that in that system, is what we should interpret as the dark energy. So now I'm going to show you again the picture of the phase space. The phase space volume I calculated is here. It's the Hicks branch, because that's responsible for the force on these variables. These are the slow variables, and they are associated with the matter. The locations of matter, positions, those are the slow variables. The force is being generated by how this big phase space back reacts on these positions. So now some people may see it coming, because I told you here is the dark energy. This is where matter will be sitting. The matter that we take out of the black hole are the eigenvalues that we take out. This is the equilibrium stuff, and that's filling our universe. This is where dark energy is sitting. So what I'm going to do next is now indeed calculate the effect of the temperature on the dynamics of the eigenvalues. So here I have the temperature of the system, or the black hole, say, and here I have these eigenvalues, and I told you the off-diagonal modes have a gravitational energy, which is this. And I already told you what are the number of eigenvalues which I have here, which is this formula. Now I'm going to do a very simple calculation. I'm going to calculate the fluctuations in the gravitational field in this system. And it's just by a partition function, where I put in the energy, which is the gravitational energy of these off-diagonal modes. I put in the temperature. Actually, I write the temperature just as T. I'm not even using any knowledge about it. I'm also not going to use anything that I know about this number n. I'm just going to say there are n eigenvalues. Because the reason why I need n is that these fluctuations would diverge in general. But since there are a finite number of eigenvalues, I have a short distance cutoff. I basically say there's a shortest distance between two eigenvalues if I know the size of the system. Take the size of the system divided by the number of eigenvalues, and this gives you the size of x cubed. So you can put it in here, or there's another way of saying it. The number of modes that we are fluctuating here, they have a finite temperature, but the number of modes is finite. It's equal to the number n, which is the number of eigenvalues. So then the gravitational energy should just be nkt. Very simple, just Gaussian integrals nkt. By the way, if I now plug this in, I get that grad phi squared equals to this number. I'm going to do this in de Sitter space. This is the temperature, that's the number of these eigenvalues, and the energy I already told you about. That's a galaxy. You're going to miss the good part. I continue. I know. These are galaxy rotation curves. This is the way you would fit them. And normally you would say v squared goes like, well, if m is sort of all visible, v squared should go like 1 over r. It doesn't. Well, you can also think about the observed v, and then you get this formula. This would be if you have the baryonic one, and this is indeed the 1 over r. But do you see dark matter coming here? There's actually a fit that people make to this constant flattening of rotation curves using the observed velocity. They write it like this. It's called the baryonic Tully-Fisher relation. It's a relation between the visible mass, so actually it's between luminosity, the light in the system and the velocity. It's this relation. It's called the baryonic one because here they replaced Tully-Fisher actually related to the light. But if you do it to the mass, you get this relation between the observed velocity and the mass. And then there's some constant that is fit. Here is sort of the fit, experimental fit. It's a over 2 pi is equal to this number. This number is very close to c times 8 naught. You may wonder why, and people don't understand it. Actually, it's the same relation that I wrote down. This is a plot. If you just calculate from observations the gravitational energy, the fluctuations, or the extra gravitational energy due to the flattening of rotation curves, and you integrate it over the size of the galaxy, and you plot it against this number n of r, which is just the mass sort of distributed, you get a straight correlation over 8 orders of magnitude. And the slope is indeed determining the temperature, and you can determine that to be the, well, if I think about n, I mean, I have to divide this by h bar, and there's something I have to fit in here because the temperature is proportional to h bar, and the number I put in is proportional to h bar, but it's the same relation that I wrote down. So the calculation I did actually fits the rotation curves. So this is my picture. Dark energy is sitting here, and there's something about dark matter here. The phase space has dark energy here, dark matter there, of ordinary matter here, and the dark matter is sort of the stuff in between. So I think dark matter may be the stuff that strings would sort of these matter particles would make when they start sort of disappearing into a black hole. I'm going to finish actually with something about this plot. I don't have a calculation that reproduces this, but I do have a picture that suggests some explanation at least of roughly where these numbers come from. Because as I told you, this is the stuff that's in equilibrium. This is the stuff out of equilibrium, and this is sort of the stuff in between. And the only thing I need to show you is some kind of idea, and you'll get the picture. If you take 1 sigma sort of dark energy, 2 sigma, and 4%. Anyhow, this is not calculated, but it's just deduced from the data. But at least this is the distribution. So I think about dark energy and matter as being part of one system, and they can interact with each other. It's one dynamical system, and what we are observing is in the tail. Our laws of physics are derived from the exception. The rule is here. And so if we want to really know what are the microscopic equations of the universe, we should describe dark energy. And not by one constant in the Einstein equation. It has dynamics. It is the energy that fuels the dynamical system that's responsible for inertia. this is where I want to end.
Thanks very much. Still, we have little time for questions.
From your proposal, can you make a prediction for what the dark matter direct detection experiment should find?
If they would find a WIMP and they explain the 23%, I would be disappointed, of course.
So a particle in an external gravitational field, I should somehow think about that gravitational field as being the result of integrating out some fast degrees of freedom that are coupled to this particle. And this temperature that you wrote was the local gravitational acceleration over 2 pi. Should I interpret that as now I'm in the sort of thermal ensemble with that temperature? What is the significance of that temperature in this picture?
I went through a whole discussion on adiabatic reaction forces where there was a phase-based definition. And if you go back there, you will find that it's not thermodynamics. It's the level density. It has to do with the number of states that you count when you change a little bit of the system. So it's a phase space. So it's not thermodynamics. I made clear it's a reaction force which are in the Born-Oppenheimer regime. So the temperature is only a measure of the energy level density locally in the number of states. And it's only when you go to horizons that you find that there is a thermodynamic interpretation. You know, I have to probably go back. I'm not sure it makes sense, but anyhow.
There's one more question.
So when you wrote the black hole, you wrote the metric. But how can you assume the metric if you are saying that gravity is the result of entropic force? I mean, metric is gravity, so then you cannot assume metric. Metric should be produced by entropy. And also the other thing is that you produced the equation that looked like Newton's gravitational equation, but can you actually produce Einstein's gravitational equation? In other words, can you not assume any metric, like you're in a flat space, start from entropy, and based on entropy in a flat space, produce Einstein's gravitational equation term by term, that the emergent metric would obey?
There exist arguments already due to Jacobson, and actually I had it in my paper 1.5 years ago, which sort of make clear why Einstein gravity you can get this from these ideas. What I try to illustrate in this talk, by the way, is a principle behind what gravity is. I'm not claiming a derivation. And in that sense, I think for me, there's no doubt that these principles apply. And what I've showed is that you can deduce new insights about phenomena from applying these principles, and they don't follow from just Einstein gravity. So this is not just another way of looking at Einstein gravity, it's another way of looking at how we should perceive matter, forces, and space-time together. It's really one system, and you should think about the emergence of those things, not from starting from flat space, but there's a very different way in which these concepts arise from a microscopic description.
Erik, if gravity is an entropic force, how should we think about gravitational waves? Would it be wrong to think about single gravitons, for example?
A graviton is like a phonon. Maybe I should leave it at that, because there's also phonons we can understand quite well as particles, but we know also that they're sort of sound waves. And so there is a regime in which the space-time indeed has waves, which we identify with gravity waves. So I'm not going to say that the gravity detector will not detect gravity waves. It still means that there can be a way of understanding gravity in the emergent form that I described it. And by the way, I already made very much clear that it's not just an entropic force. It's really, I think, the more precise way of saying it's an adiabatic reaction force, which in some regime looks like a Born-Oppenheimer force, and another regime is more like the entropic force. So depending on the separation of timescales, there's actually a difference, sort of a qualitative difference in those two situations. But quantitatively, they're described by the same equations.
Okay, next question.
Well, yes. In some more conventional approaches to physics, we think we know how to manufacture cosmological models with different amounts of dark matter, different amounts of baryon density. Are you saying those are internally inconsistent, or what?
As I told you, this is a different paradigm, and I think it's true that certain frameworks cannot make predictions and others can. So the fact that we use effective field theory, for me, the motivation, even the justification of effective field theory is the Wilsonian framework, and there you do not assume to know everything about the UV. It's clear that gravity knows much more about the UV than we normally do in conventional quantum field theory frameworks. So I think understanding the connection between the UV physics and the R physics may shed light on questions which you cannot obtain from just Wilsonian type quantum field theory.
So you are saying they're internally inconsistent then?
I think they're only consistent as effective field theories, which is also their only reason for existence.
Okay, so maybe we should stop here. Let us thank Erik again.